Hi everyone, it's the Math Sorcerer here with Chegg. In this video, we're going to discuss Stokes Theorem. So Stokes Theorem is this piece right here. It basically says that the line integral over C of f dot dr is equal to the surface integral over S of curl f dot ds. S here is the surface, and it is positively oriented and piecewise smooth. C is also positively oriented, and it is the boundary of that surface. So Stokes' theorem creates a relationship between line integrals and surface integrals. Over here on the right, we have a double integral over d of curl f dot, and we have the vector negative g sub x, negative g sub y1, and then dA. So this is a formula that is found in most textbooks. Sometimes you have to hunt for it, but this is the one we're going to use. Basically, we're going to do an example where we compute f dot dr over c, and we're going to use this formula here, because curl f dot ds is basically equal to this double integral as long as your normal vector is pointing upwards. So this is your normal vector, and the orientation is up. So if that's the case, you use this formula. If the orientation is down, there's a very similar formula. Let's go ahead and do an example right away and go over what everything is again in our example. We're going to evaluate the line integral of f dot dr, where f of x, y, z is equal to y squared I hat plus z squared j hat plus x squared k hat. And c is the triangle that has vertices 1, 0, 0, and 0, 1, 0, and 0, 0, 1. Let's go ahead and work it out. Solution. We'll start by computing the curl of our vector field f. So recall the curl can be memorized by memorizing a particular determinant. We have this determinant, and the first row is I hat, j hat, k hat. The second row just has partial derivatives, so del x, del y, del z. And the third row has the actual components of f. In this case, it'll be y squared, z squared, and x squared. So let's fill those in: y squared, z squared, and x squared. So very convenient: ijk, the partials, and then the components of your vector valued function. I went ahead and worked out the curl, so let me explain this equation. We start by crossing out the first row and first column in our determinant, and then you multiply del y of x squared, which we have over here, minus, and then del z of z squared, which we have over here. So again, cross out that first row, first column, and then it's del y of x squared, and you always put a minus, and then it's del z of z squared. Then you put your I hat. Notice it's plus, minus, plus. That's the pattern. Now let's go to the next term. For this one, we cross out the first row, second column. So it's del x of x squared, which we have here, check, minus del z of y squared, which we have here, check. Then you put your j hat, very nice. And it's plus, and then we cross out the first row, last column. So that will be del x of z squared minus del y of y squared, which we have here, and then you put your k hat. So all is good. Then we have that the curl of f is equal to, so when we're computing partial derivatives, remember that all of the other variables are constants. For example, del y of x squared is going to be 0 because we treat the x as a constant. Whereas here, del z of z squared is simply 2z, and we have our I hat. Minus, parentheses, del x of x squared is 2x, minus, and then del z of y squared, that's 0 because we're treating the y as a constant. You treat all other variables besides z as constants, so that's 0. Then we have j hat. Plus del x of z squared is 0, minus, and then del y of y squared is 2y, and then we have our k hat. So we end up with the curl of f is equal to negative 2z I hat, negative 2x j hat, minus 2y k hat. And I'm going to write this in component form because it will make life just a little bit easier. It looks better. So this is the vector with components negative 2z, negative 2x, negative 2y. So we wrote the curl of f as a vector with these components. Now that we have the curl of f, we need to pick a surface so that c is the boundary of that surface. So I've picked S, which is the plane x plus y plus z equals 1. So this is a plane that contains our triangle which you see here pictured on the screen, and you can see the positive orientation of the triangle indicated in red. Now we need to find g for our formula. So to find g, we basically solve the equation x plus y plus z equals 1 for z. When you do that, you get z equals 1 minus x minus y. And this is the same thing as g of xy. Now let's compute the partial derivatives of g because we need them for our formula. So g sub x is equal to -1. That one's pretty easy because the derivative of 1 and -y are 0. Likewise, g sub y is -1. So our vector that we're going to use for our formula, so instead of negative g sub x, we're going to put 1. Instead of negative g sub y, well, it's already a -1, so it becomes a 1. And the last component is 1. So I'm going to put this in a box because this is something that we're going to use in our actual formula to finish up the problem. So we have the vector 1, 1, 1. We have the curl of f. We're almost ready to do the integration, except if you look at the curl of f, you'll notice that the curl of f has a z in the first component. It says -2z. So what we need to do is we need to replace that z with 1 minus x minus y. So the curl of f is equal to -2 times z, which has been replaced with 1 minus x minus y, comma -2x, comma -2y. All right, let's go ahead and recap everything we have and finish up the integration. So we have the line integral over c of f dot dr is equal to the double integral over d of the curl of f dotted with the vector whose components are -g sub x, -g sub y, and 1 dA. This is equal to the double integral. And for the curl of f, we have the vector with components -2 plus 2x plus 2y, comma -2x, comma -2y. I just did a little bit of simplification, just multiplied the 2 through. And this other vector, -g sub x, -g sub y, comma 1, is just the vector 1, 1, 1. And now we're going to set up the limits of integration. So here you see how we've drawn the picture. We've got the plane x plus y plus z equals 1. So if you set z equal to 0, you get x plus y equals 1, and you can solve for y, and you get y equals 1 minus x. So if we first integrate with respect to y, we're going to go from 0 to 1 minus x. And then with respect to x, we're going to go from 0 to 1. And those are our limits of integration. Continuing with the integration, we have the definite integral from 0 to 1, the definite integral from 0 to 1 minus x, and now we're going to compute the dot product. We first multiply the first components. So -2 plus 2x plus 2y times 1 gives us -2 plus 2x plus 2y. Then we do -2x times 1, that gives us -2x. Then we do -2y times 1, that gives us -2y, and we still have the dy and the dx. So it's equal to the definite integral from 0 to 1, the definite integral from 0 to 1 minus x of -2 dy dx. That's just the integral from 0 to 1. We integrate the -2, so we get -2y, and we go from 0 to 1 minus x, and we still have the dx. You first plug in the 1 minus x, so this is the definite integral from 0 to 1. -2 parentheses 1 minus x, subtract and plug in 0 so it goes away, and so we simply have dx at this point. We distribute the -2 and we get the integral from 0 to 1 of -2 plus 2x dx. Integrating, we get -2x plus 2x squared over 2, so it's just x squared, and we're going from 0 to 1. You plug in the 1 first, so you get -2 plus 1, subtract, plug in 0, so it goes away. You end up with a beautiful answer of -1. As you can see, Stokes Theorem usually takes a lot of work. I hope this video has been helpful, and hopefully you've learned some mathematics. If you enjoyed this video, make sure to check out more videos on Chegg. Until next time, good luck.